This is the 16th video in our series on abstract algebra. And today we're going to look at a really important theorem that helps us classify finite abelian groups. And in fact, this is called the fundamental theorem of finite abelian groups. And it says that if G is a finite abelian group, then G is isomorphic to ZP1 to the A1 cross ZP2 to the A2, all the way up to ZPN to the AN. And this is for not necessarily distinct primes PI, and then natural numbers AI. Okay, so we can't prove this without quite a bit of preparation, and we're gonna put that preparation into the form of some lemmas that go in the correct direction. Starting with the following lemma. It says that if G is an abelian group, the order of G is n, and then P is a prime that divides n, then G indeed has an element of order n. Okay, nice. And we're going to do this by induction on the size of the group. So, like I said, induction on n. Okay, so that means we're going to need a base case, and then after that we'll need an induction hypothesis. So let's observe that the base case here is like pretty boring because that is n equals 1. But no primes divide 1, so you can't really get out of the gate here. That tells us that G is the trivial group. Now it's not necessary that we look at another base case, but just to keep it interesting, let's take n equals 2. But if n equals 2, that tells us that G is isomorphic to Z2, because there's only up to isomorphism one group of order 2. But let's notice that the only prime that divides 2 is 2, and we definitely have an element that has order 2 within this group, and it's the number 1, or the non-identity element, if you will. Okay, so that's our base case. Now let's make an induction hypothesis. And this will be a strong induction hypothesis. So let's suppose for all m between 1 and n, but not including n, that the statement holds. And then where do we want to go from there? Now let's suppose that we have a group G with the order of G equals n. So it's the first order after our induction hypothesis holds. And now we're going to split this up into a couple of little cases. So our first subcase will be the case if G has no proper subgroups. Okay, so let's look at that case. So we know that if we have a non-identity element in G, that the cyclic group generated by G is a subgroup of G. Well, but it's not the identity subgroup because that's not equal to the identity, but since G has no proper subgroups, that has to be equal to the whole group. But now let's put a cyclic subgroup on the left of this, and that'll be the cyclic subgroup generated by G to the n over P, where n and P are defined up here. N is the order of the whole group, and P is that prime. Okay, so that's definitely a cyclic subgroup of this G group. Okay, but then we have the identity subgroup living over here on this side. And then we have really only two cases here. And that's because we've assumed that there are no proper subgroups, and that means that either these are equal or these two are equal, because we can't have anything strictly between those two. Okay, but let's look at each of those cases. So if these two are equal, then we have G to the n over P is the same thing as the identity, but that means that n divided by P is a multiple of n just by order considerations. But the only way for n over P to be a multiple of n is for P to be equal to 1. But that's most definitely a contradiction because 1 is not a prime. So that means this blue underlined stuff must be the true statement. This was not possible, so that means this is possible. Okay, but then if these are equal, then we can calculate the order of each side. So we have the order of g to the n over p must be equal to the order of g. Okay, but the order of g is the whole group order just based off of our assumption of this no proper subgroup thing. So we know that this is equal to n. But then the order of g to the n over p, well, we have like a formula for that from a while ago when we were studying cyclic groups on their own, and that was equal to, let's see, it was equal to p. So following this from the left to the right, we see that n is equal to p. But what does that mean? Well, that means that we found an element of order p. It just happened that the order of the whole group was also order p. Okay, so now let's move on to our second case. So if our first case was that G did not have a proper subgroup, then our second case must be that G does have a proper subgroup. So let's call that subgroup H, and let's calculate its order. So we know that the order of H must be strictly bigger than 1, because if the order of H was equal to 1, then it would not be a proper subgroup. And it has to be strictly less than n, because again, if the order of H was n, then it would also not be a normal subgroup. And then let's also notice that since we are within an abelian group, we know that H is normal in G. And now from here, we're going to split this into two cases. So let's lay those cases out, and it has to do with the divisibility of the order of H by P. So if P divides the order of H, then by the induction hypothesis, because the order of H is strictly less than the order of G, we have some element which I'll call little h in H, where the order of little h is equal to P. Like I said, that's applying the induction hypothesis to our group H. If P does not divide the order of H, then actually P divides the order of this quotient group G mod H. And let's give a little explanation to that. Notice that we know that n is equal to the order of G, but that's also equal to the order of H times the order of G mod H. That's by Lagrange's theorem. But if P divides n and P does not divide H, then we know that P must divide the order of that quotient group. Okay, so that's good. So now let's apply the induction hypothesis to the quotient group. So that quotient group being G mod H, and so that gives us some element which I'll call GH. Remember, it has to be a coset. So GH in G mod H, such that the order of GH is equal to P. Great. And again, that's by the induction hypothesis, because notice that the order of G mod H is strictly less than the order of G. So the induction hypothesis is satisfied here. Okay, nice. But now, since we know the order of GH is equal to P, we know that GH cannot be equal to the identity coset. So like I said, GH is not equal to the identity coset. And that's because if this were equality, then the order of GH would be equal to 1 and not P. But these cosets being unequal tells us that G cannot be an element of H. Okay, so that's good. And now let's do our calculation. And this calculation will essentially finish it off. So we have EH is the same thing as GH all to the P power, just given the fact that the order of GH is P. But then that's equal to GPH by the group rule inside of the quotient group. But this coset being equal to this coset means that GP is indeed an element of H. And now that we have this, we're almost to our element of order P, but we're not quite there yet. Let's introduce a little bit more notation. Let's set the order of H equal to M. And then since g to the p is in h, that means g to the p all raised to the m power is equal to the identity. Because anytime you take an element of a group and you raise it to the order of the group, you get the identity. And now let's rewrite this as g to the m all to the p power equals the identity. Okay, nice. And now we'd like to make the following claim, and this claim will finish it off. So our claim is that the order of g to the m is equal to p. Okay, and we're going to do this by way of contradiction. So by way of contradiction, suppose that the order of g to the m is not p. But if the order of g to the m is not p, because p is a prime, we know that the order of g to the m must be equal to 1. In other words, we have g to the m is equal to the identity. Okay, great. And then let's also note that the GCD of m with p is equal to 1. And let's talk our way through that. So we know that p does not divide the order of h, but we called the order of h m, so that means p does not divide m. But if p is a prime and it doesn't divide m, that means the GCD of mp is equal to 1. But that means that we have mx plus py is equal to 1 for some integers x and y. So that's by like Bézou's lemma. Okay, and now we're pretty much ready to finish this thing off. Let's take g to the first power and rewrite it as g to the m raised to the x times g to the p raised to the y. That's just like using exponent rules along with this formula right here. Well, notice that by way of contradiction, we suppose that g to the m was the identity. So this bit right here is simply the identity. So this is the identity. And then g to the p is an element of h from this line right here. So we've got the identity times something in h, which I'll call just like little h for now. But that means we've got an element of h. So that means g is an element of h. But let's see, I think somewhere we said that g is not an element of h. That's right here. So that leads us to a contradiction. But what did we contradict? Well, we contradicted the fact that the order of g to the m was not equal to p. So that means the order of g to the m must indeed be equal to p, which means that we have an element of order p finishing this off. Now let's move on to our next lemma. So for our next lemma, we're going to need a quick definition. So we say a group G is a p group if for all elements of G, the order of the element is a prime power, where that is a fixed prime. So a 3 group would have elements only of order 3, 3 squared, 3 cubed, so on and so forth. Of course, I'm talking about non-identity elements here. Okay, and then the lemma says that G is a finite abelian P group if and only if the order of G is a power of a prime, or a power of that prime, I should say. Okay, so now let's do the forward direction of this proof first, and we'll do this by the contrapositive. So let's suppose that P and Q are distinct primes such that P divides the order of G and Q divides the order of G. Let's talk about why this is the contrapositive. Well, if we're assuming that this is not true, so the order of G is not the power of a prime, then that order must have 2 prime factors, and that's what we're saying here. Okay, great. But now let's apply the previous lemma, so the one we just got done proving, to find something that I'll call x and y inside of G, such that the order of x equals p and the order of y equals q. Remember, that was possible exactly by that last lemma. But that means not everything has the order which is the power of this prime, which tells us that we don't have a P group. So G is not a P group. Okay, nice. Now let's do the reverse direction. And this reverse direction will be done with just like a straightforward proof, so the method of direct proof. Okay, so let's suppose that the order of G is a power of a prime, so P to the n, and we also have an element G inside of G. Now we want to show the order of the element is also a power of this prime, but this is pretty straightforward, and we can do this by the duality between an element and the cyclic subgroup generated by this element. So let's notice that the cyclic subgroup generated by G, well, that's a subgroup of G, but then by Lagrange's theorem, the order of this cyclic subgroup divides the order of the whole group. That's an application of Lagrange's theorem. But that means that the order of the element divides the order of the whole group, which was P to the n. Okay, but if something divides P to the n, where P is a prime, then that means that that something is the power of that prime. So in other words, the order of G is equal to P to the m, where m is between 0 and n. But that means that G is a P group. So that finishes this proof off. Now let's move to the next lemma. So for our next lemma, let's let G be a finite abelian group of order P1 to the R1, P2 to the R2, all the way up to Pk to the Rk. So you could think about this as the prime factorization given by the fundamental theorem of arithmetic for the order of G. And so that means we can take the primes to be distinct. Then G is isomorphic to G1 cross G2 all the way up to Gk, where these Gi's are groups of order Pi to the Ri. So it somehow captures all of the like primeness or all of that primeness. Okay, so we're going to first build the Gi groups, and these will in fact be subgroups of G. So let's set Gi to be all elements little g in G, where the order of that little g is a power of that prime Pi. And now let's notice that we initially have to show that these are subgroups. A priori, we do not know that these are subgroups. Okay, so let's show that they're subgroups. Well, so first of all, notice that the identity is most definitely an element of Gi. And let's check why that's the case. And that's because the order of the identity is equal to 1, but 1 is equal to Pi to the 0 power. But that's a power of the prime, which means we have the entry fee for the identity to get inside of Gi. So now let's move on. And instead of using the subgroup test here, I'm just going to use the definition of a subgroup. So let's next suppose that x and y are in Gi, but let's notice that that means that the order of x is equal to Pi to the m for some m, and the order of y is equal to Pi to the n for some n. Again, that's the entry fee to be inside of Gi. And then also, let's notice that the order of x times y is equal to the LCM of the order of x and the order of y. So this is a standard result on abelian groups. Okay, but that's the LCM of Pi to the m and Pi to the n. But if you take the least common multiple of the power of a prime, or really two powers of the same prime, you just get the maximum power that you see. So let's take Pi to the maximum of mn. But that means that xy has the correct order to be inside of Gi, so that means that xy is indeed an element of Gi. So that means Gi is closed. Okay, so the next thing that we need to do is show that we have inverses, but this is pretty straightforward as well. So let's suppose that x is in GI, but that means that the order of x is equal to pi to some power n. But then also, we know that the order of x inverse is the same thing as the order of x. So that's a pretty standard result from way back in the course. So that means the order of x inverse is also pi to the n. Oh, but that means that x inverse is also inside of GI. So that means GI has the identity, it has closure under the group operation, and it has inverses. So that means that these are indeed subgroups. So let's add our subgroup symbol there and then move on to the next step. Now that we've got a collection of subgroups of G, we're going to show that they intersect trivially. And we'll do this by taking an element from an intersection of any of the two pairs and showing that that element has to be the identity. So let's suppose that G is an element of GI intersect GJ. And that's where I and J are not equal. Okay, so that means that the order of G is equal to pi to the m. That's because GI is in GI, and the order of G is equal to pj to the n. That's because G is in GJ. Okay, but now putting this together, that means that pi to the m is equal to pj to the n. So the power of one prime is equal to the power of another prime, but these are distinct primes. And the only way for two distinct primes to exponentiate to the same number is if their exponents are 0. So that means we have m equals n equals 0. But that means that the order of G is pi to the 0 or pj to the 0. But that means that the order of G is equal to 1. But there's only a single element with order 1 and it is the identity. So that means we have G as the identity. So we took something in the intersection, showed it had to be the identity. So that means that indeed we have GI intersect GJ is just the identity. The intersection is trivial. Okay, so now let's move on. So next up, we're going to show that their product is everything. And by that, I mean that G is equal to the product of these subgroups, G1, G2 up to GK. But their product being everything and them intersecting trivially means that G is an internal direct product, which is isomorphic to an external direct product by previous results. So that means once we're done showing that their product is everything, then we're done with the whole thing. Okay, so let's suppose that we've got an element little g inside of G, and then essentially we're gonna factor this into parts from G1, G2 up to GK. Okay, but now let's note that the order of little g must divide the order of the entire group. But the entire group is this right here. So the order of little g must divide p1 to the r1 multiplied up to pk to the rk. So now let's introduce a new set of numbers. And those numbers I'll call ai, and it'll in fact be this product right here, but without the ith term. So I can write that as p1 to the r1 multiplied all the way up to pi minus 1 to the ri minus 1, and then pi plus 1, ri plus 1, all the way up to pk to the rk. So notice that this is in fact simply the order of the group divided by pi to the ri. So either way you want to look at it. Okay, nice. But now let's also notice that the GCD of all of these numbers that I'm making like this is 1. And I don't mean like the pairwise GCD, but the total GCD. So the GCD of A1, A2, all the way up to AK is, like I said, in fact equal to 1. That's because P1 does not divide A1, P2 does not divide A2, P3 does not divide A3, so on and so forth. So you can't find anything that divides all of them except for the number 1. But now we're going to apply our Bézout's formula to this GCD problem. It's just like kind of bigger than this case. So let's find these numbers that I'll call BI, which are integers, such that A1, B1 plus A2, B2 all the way up to AK, BK is equal to 1. So you can do that with larger GCDs, not just GCDs of 2 numbers. Okay, so now we're essentially ready to get to it. Let's take G to the first power, which is equal to G, and then we'll write 1 using this formula. So this will be G to the A1, B1 times G to the A2, B2, all the way up to G to the AK, BK, where I split it up using exponent rules. Okay, but now I'm going to say that this is equal to G1, G2, all the way up to GK, where each of the GI's are these corresponding parts right here. So we have GI is equal to G to the AI, BI. Okay, so I think that's looking good. But now let's notice that little gi to the power p to the ri, or I guess I said pi to the ri, is equal to little g to the power, let's see, ai times pi to the ri times bi. But now notice that ai times pi to the ri by this formula right here is simply the order of the group. So this is g to the order of the group, all raised to the bi power. But then by a result of Lagrange's theorem, anytime you take an element of the group to the power of a group, you get the identity. So this gives you the identity. But notice that this raising of gi to this exponent and getting the identity is exactly the entry fee to be inside of gi. So that means that here we have gi is inside of gi. So, you know, we've essentially done it here. We have little g is equal to g1, g2 up to gk, but we just showed that each of these gi's are in the capital GI, which means this product right here is in g1 up to gk. And like I said before, because these intersect trivially, we have that this G is an internal direct product of all of these groups, but that's isomorphic to an external direct product of all of these groups. And that's exactly where we wanted to end. Now we've got our final and most intricate lemma, but good news, after proving this lemma, the proof of this big theorem over here will be quite short. So let's see what we have. Let's let G be a finite abelian P group, and let's take little g and G with maximal order. Then G is isomorphic to the cyclic subgroup generated by G cross K, where K is some other subgroup of G. And the method of proof here will be induction on N, where the order of G is equal to P to the N, which, recall, that's equivalent to having a finite abelian P group, is having the prime order for the size of the group. Now, let's observe the base case is super easy. If n is equal to 1, then the order of G is a prime. But previously we showed that all groups of prime order were cyclic groups, and they were isomorphic to ZP. So let's just take any generator of the group G. You know, it's cyclic, so it has a single generator, and then we'll cross that with just the identity subgroup. And that's essentially all there is to it. And then maybe I should have an isomorphism here. Okay, so like I said, the base case is pretty much done. Now let's make our induction hypothesis. And this will be another strong induction hypothesis. So let's suppose for all m between 1 and n, but not including n, we'll say the result holds for groups of order p to the m. Okay, that's good. Now let's suppose that we've got a group G which is order p to the n, and then take an element G in G such that the order of G is maximal. So this is totally possible because if you run through the order of every element in a finite group, you get a finite set, which means you can just take the maximum value of the finite set. And then you can just like pick any of these group elements that achieve that maximum value. Okay, nice. But now let's notice that the order of an element divides the order of a group. The order of a group is a power of a prime. That means the order of the element is also the power of a prime. Well, the same prime, in fact. So we have the order of G is equal to P to the K, where, like I said, K is as large as possible. So let's write that down, as large as possible. But notice it definitely can't be bigger than n because you can't have an order of an element be larger than an order of a group. But it could be up to n if we have, in fact, a cyclic group. Okay, and let's actually look at that edge case. So if k is equal to n, well, then that means you have the order of little g is the same thing as the order of the entire group, which tells us that this group is cyclic and generated by little g. But, you know, that's isomorphic to the group little g cross the identity subgroup. So we've achieved our goal. So that means what we want to do from here is suppose otherwise, because this case isn't really that interesting. So otherwise, we would have k strictly less than n. And then we're going to take a element that's kind of dual to G. G was chosen so that it has maximal order. And now let's choose H, and H will be outside of the cyclic subgroup generated by G of minimal order. So notice it's in the group, but outside the cyclic subgroup. So of minimal order. Great. And that's sort of the setup to get started. Well, let's maybe clean up the board and then we'll start from that setup. So just to remind ourselves, we took an element G from G that had order P to the K, where K was chosen to be as big as possible. And then we chose an element H outside of that cyclic subgroup to have minimal order. Notice H cannot have the identity because the identity is inside of that cyclic subgroup. So H has order which is larger than 1. It's another power of a prime, in fact. And now the first thing that we want to do is actually determine what the order of H is. Okay. So let's notice that there are some things that we immediately know. Notice that the order of H is a power of a prime. And that's because it has to divide the order of the whole group. H is inside the whole group, so we know that. And furthermore, we know that this is less than or equal to P to the K. In other words, R is less than or equal to K. And we know that because P to the K is the maximal order. So if the order of H is P to the R, then from that it follows that the order of H to the P is P to the R divided by P. In other words, P to the R minus 1. And that's by some rules that we proved quite a while ago. Okay, nice. But notice the order of H to the P is strictly less than the order of H. Okay, but what does that mean? Well, that means that H to the P must be inside of this cyclic subgroup. So again, that's by the minimality of the order of H, the way that we chose it. Okay, so we've got H to the P is inside of this cyclic subgroup. Okay, but what does that mean? That means that we have H to the P is equal to G to some power. Well, that's what it means to be inside that cyclic subgroup. And this is for some A bigger than or equal to 0. So we're in a finite group, so we can take only non-negative exponents if we want to. And now we're going to play a bit of a game. So let's take G to the power A, and we'll raise that to the P to the K minus 1. And let's observe that that's the same thing as H to the P raised to the power P to the K minus 1, just by this equation right here. Okay, but notice that that simplifies to h to the p to the k. Okay, but notice that p to the r divides p to the k. So we're raising h to a multiple of its order. But that means that we get that this is simply equal to the identity. Okay, but from this, we get that the order of g to the a is at most p to the k minus 1, because we just raised g to the a to the p to the k minus 1 and got the identity. So that means this is less than or equal to p to the k minus 1, like I have just said. Okay, but then where can we go from there? But now, since g to the a does not achieve the maximal order, that in fact tells us that p must divide a. And why is that? Well, let's recall this little formula right here. We have the order of g to the a is equal to the order of g divided by the GCD of the order of g and a. Okay, nice. But notice that this GCD cannot be 1. Because if this GCD were 1, then the order of g to the a would be equal to p to the k. But we just said that it's less than or equal to p to the k. So, like I said, this GCD is not 1. But the only way to have a GCD that is not equal to 1 with a prime power is for that prime to divide into u. So that's a lot of kind of number theoretic games, but it ends with p dividing a. Okay, but from that we can see that a is equal to p times s, where s is some number. Okay, nice. But now let's insert that back here. Okay, so that means what do we have? We have h to the p is the same thing as g to the ps. Now let's move some things around and we get a pretty interesting equation. And that interesting equation goes like this. We have g to the minus s times h raised to the p power is the identity. Okay, so that's just like, I don't know, left multiplying by g to the minus sp on both sides, and then using some like exponent type rules. Okay, so next up, we would like to set x equal to this element that is being raised to the p power and getting the identity. So it's g to the minus s times h. So it's that. And then let's notice that we have x to the p is equal to the identity. Well, maybe first off, let's notice that x itself is not the identity. And how do we know it's not the identity? Well, if it were the identity, then h itself would be inside of this cyclic subgroup generated by g, but that was one of our original assumptions. So we have x to the p is the identity, but x is not the identity. But since p is a prime, that tells us that the order of x is in fact equal to p. But that's the minimal possible order of a non-identity element, given that p is a prime. Oh, but we chose h to have minimal order outside of that cyclic subgroup. But x is also outside of this cyclic subgroup. But that means that h must match this minimal order. So in the end, we get that the order of h is in fact equal to this prime. Okay, nice. Now let's move on to the next part. So now that we've determined the order of h is p, we want to look at the intersection of the cyclic subgroup generated by g and the cyclic subgroup generated by h. So g was chosen to have maximal order, and h was chosen outside of the group generated by g to have minimal order. So here we're playing this like maximal minimal game between these two things. Okay, so like I said, we want to find the intersection, and what we'll do is start with something inside the intersection and indeed show that that something in fact has to be the identity. So what we're showing is that these intersect trivially. Okay, so we've got y in the intersection of those two, but that means that y is in the cyclic subgroup generated by h. but that means that y can be written as h to the a, where a comes between 0 and p minus 1. So this is a cyclic subgroup of p elements. So that means that everything in that group can be written as a to the a, where a is between 0 and p minus 1. Okay, nice. So now if a is not equal to 0, then what do we have? We have the GCD of a with p is equal to 1. That's because a is between 0 and p minus 1, and p is a prime, so that's pretty clear. And now we're going to take two numbers, I'll call them u and v, or maybe we'll call them r and s, they are integers, such that we build a GCD equation like using Bézou's lemma. So in other words, we have AR plus PS is equal to 1. So of course, between the steps, I'm like resetting the values of all these constants or whatever. So this is a new A, these are new R's and S's. So just keep that in mind. But now what are we gonna do from there? Now we're gonna do the following calculation. So let's see, let's do y to the r power. But notice that y to the r power is the same thing as h to the a raised to the r power. Oh, but that's equal to h to the ar. Oh, but now we can use this equation right here to rewrite this as h to the 1 minus ps, which is h times h to the p to the minus s, using like group laws. But recall that h to the p is the identity given that the order of h was p. We proved that on the last board. So that means this is exactly equal to h. But let's notice if y is in this intersection, then any power of y is also in this intersection. In fact, y to the r must be in this intersection. But that means that h is in this intersection. In particular, h is in the cyclic subgroup generated by g. But that's a contradiction because that was one of our assumptions on how we built h in the first place. But what does that tell us? That tells us that it's impossible for a to not be equal to 0, which means that a must in fact be equal to 0. But now throwing that back into the way that we built y over here with h to the a, that means that y is equal to h to the 0, which is the identity. So putting this all together, we see that this intersection must be trivial because we tried to find something in the intersection and we showed that that something really had to just be the identity. Okay, so now that we know these intersect in just the identity, we can move on. Okay, I've summarized what we've done up here, and now we're ready to start doing fancy stuff with quotient groups. In particular, we want to look at the order of the coset GH inside of G mod H, where I'm setting this capital H to be equal to the cyclic subgroup generated by little h. Let's maybe quickly notice that we actually know something about G mod H already. We know the order of this group. So let's point out that the order of this group is p to the n minus 1. That's because the order of G is p to the n and the order of H is p by what we said before. Okay, so now let's get to it. So let's maybe set R equal to the order of GH. And notice that I think it's pretty clear that the order of a coset inside of a quotient group must divide the order of the coset representative inside of the whole group. So that's a good thing to start with. Next up, let's also do the following calculation, which will actually get the divisibility relationship in the other direction. So we've got G to the RH is the same thing as GH to the R, but that being defined to be the order of GH will give us the identity coset. But from that, it tells us that G to the R is in H just by coset equality. Oh, but notice that that tells us that G to the R is in the cyclic subgroup generated by G and the cyclic subgroup generated by H, given the fact that it's a power of G and then H was the cyclic subgroup generated by H. Oh, but check it out. We just proved that that was in fact the identity. So taking this to the end, that tells us that g to the r is equal to the identity. But that tells us that the order of g divides r from a result from like video 4 or something. So let's see what we have. We have r divides the order of g, and the order of g divides r. So that means, in fact, the order of g is equal to r, which is the order of gh. But then we wrote that the order of g was p to the k. That means the order of gh is also p to the k. So we just showed that the order of the coset gh was p to the k. But let's notice that that is the maximum possible order of an element in this quotient group. And that follows from the fact that the order of an element of a quotient group divides the order of the corresponding element, or really collection of elements inside of the original group. So that tells us the maximum possible order inside of G mod H is the maximum possible order of something inside of G, which was p to the k. Okay, so anyway, we've got the order of GH is p to the k. Oh, but that's really great news, because we've achieved an element of maximal order inside the quotient group. So now we'll do some quotient group argument where we apply the induction hypothesis to this quotient group, which has an order strictly less than the order of the original group, so the induction hypothesis applies. So what does that tell us? That tells us that we can write G mod H as the cyclic subgroup generated by GH cross K mod H. Well, you might look at this and say, okay, well, I get this part here. This is a cyclic subgroup generated by an element with maximal order, and that's exactly what we have here. GH has maximal order inside of this. But over here, I've just got some subgroup of G. And here, shouldn't this just be some subgroup of the quotient group? But in the last video, we looked at this fourth isomorphism theorem, and that said that every subgroup of the quotient group was of this form. So that means we can just slap a subgroup of that form right there and call it good. And then I'd like to maybe point out that we know something here. We know that H is a subgroup of K, and then like we had before, K is a subgroup of G. So again, that's by the fourth isomorphism theorem. And now we're going to pull this result back to the original setting. And we're going to do that with the following claim, which will essentially finish this whole thing off. And that is that G is isomorphic to the cyclic subgroup generated by G cross K, where K is this subgroup from this quotient right here. Okay, and we'll do this by showing that in fact we have an internal direct product, but if we have an internal direct product, then by design we have an external direct product from previous results. Okay, so that means we need to show that these intersect trivially. So that'll be the first part of this claim. The cyclic subgroup generated by G intersected with K is simply equal to the identity subgroup. Okay, nice. So how could we do this? So let's suppose that we've got some X which is in this intersection. Okay. But notice that means that if we pass to the quotient group, we have XH is inside of the cyclic subgroup generated by H intersected with this K mod H. But then by this isomorphism kind of in reverse from external direct product to internal direct product, we essentially know that these intersect trivially. So this intersects to the identity within the quotient group, which is EH. But if XH is equal to EH, then that means that X is, in fact, inside of H. Okay, but notice by this assumption right here, it's also inside the cyclic subgroup generated by G, but we showed up here that those intersect trivially, so that means that X must just be the identity. Okay, so we've shown that they intersect trivially. Great. And then we finish this thing off with showing that G is the internal product of these two subgroups. So in other words, it's of the form cyclic subgroup G, K. And then, of course, applying that theorem that I've been talking about takes us here. Okay, good. So let's get to it. So we're going to do essentially the same thing. Let's take an X inside of G. And notice that that means that the coset XH is inside of GH. But again, applying this sort of like external to internal direct product thing in reverse, this is equal to the internal product of the cyclic subgroup generated by GH and the quotient subgroup K mod H. But notice that means that XH has a certain form, and that form is G to the R times little KH, where G to the R is in that cyclic subgroup, and then K comes from K. But now these equalities of cosets in fact tell us that X is from the coset GRKH. Again, we use this equality of cosets theorem a ton of times. This is just another application of this. But now this is really good news. H is a subgroup of K, so that essentially takes it home. So this right here will be a subset of the cyclic subgroup generated by G and then K. And that's because G to the R is in that cyclic subgroup, and then K is in K, and H is a subgroup of K, so that takes us home. Okay, but then what did we do? We took an X and G and showed that it had to be in this setup. Okay, cool. So now let's review what we have and make sure that everything is in order. We just showed that these two subgroups intersect trivially, and the entire group is a product of these two subgroups. But that means the entire group is an internal direct product of those two subgroups, but that means it's isomorphic to an external direct product of those two subgroups. But that takes us exactly to our result. Okay, so now let's apply all of this to our big theorem. Now this proof is going to be quite quick. So notice that we can immediately write G as G1 cross G2 cross all the way up to GK, where we have the order of GI is equal to PI to the power RI. So again, that's because G is a finite abelian group. That's from one of those lemmas that we had before. Okay, so now we'll apply the immediately previous lemma to each GI. So notice that we can write each GI as, let's see, the cyclic subgroup generated by little gi cross hi, where hi is a subgroup of gi. And now here we'll say that the order of gi, and in fact, this is a bit annoying, but we kind of have to superscript this with a 1. So the order of gi1 is a power of a prime. So this is pi to the si1. Okay, nice. But notice that immediately tells us that this cyclic subgroup is isomorphic to z pi to the si1. And now we can split that off. So that means we have gi is isomorphic to z pi to the si1 cross hi. And now we're just going to play this game again. And I guess if you really need to, you can superscript this with a 1 because we're counting it like that. So now apply that again to this hi. And then apply it again to the thing that happens after that, and the thing that happens after that, and the thing that happens after that, and so on and so forth. And what you'll end up with is ZPI SI1 cross all the way up to ZPI to the SI. I don't know, you need an ending point here. Let's just put M. Great. So that means each GI is some sort of direct product of these ZPI groups. But then smushing it all together and then rewriting things a little bit more nicely, you get something like this. Okay, so let's look at some applications and then we'll be done. So for our two examples, we'll find all abelian groups of order 8 and then also of order 300. Well, let's notice that 8 is equal to 2 cubed. We're going to apply this result over here. So these should be products of these ZP type groups. Furthermore, we know that the p's in all of these cases here will be equal to 2 because 2 is the only prime dividing into 8. So I'm going to outline my strategy for this. So what I like to do is start with Z2 cross Z2 cross Z2. So in other words, all of the prime factors like spread out as much as possible. And then from there, I'll combine them. And that will give you non-isomorphic groups if you combine two prime types together. So we know that this is inherently different than Z2 cross Z4. That's from combining the two Z2s. You're not really combining the two Z2s. This is just how I keep track of things. And then you get one more from combining again, and that'll give you Z8. And so altogether, that's the only way of writing 8 with factors of 2. So you get 1, 2, 3 abelian groups of order 8. Now let's look at abelian groups of order 300. That's 2 squared times 3 times 5 squared. So I'm going to play the same game again here. So let's start with Z2 cross Z2 cross Z3 cross Z5 cross Z5. Okay, and then let's push two of the primes together, maybe one at a time. So if we push the two 2's together, we get a different group, Z4 cross Z3 cross Z5 cross Z5. And then if we likewise leave the two 2's apart and push the two 5's together, we will get Z2 cross Z2 cross Z3 cross Z25. So that's different from this. And then if you push both of them together, you'll get Z4 cross Z3 cross Z25. And that's the only way of factoring these 2's and 5's into this abelian group setup given by this theorem over here. Okay. But sometimes there's like another kind of logical choice for writing these groups, given the fact that we can push things together if the GCD is 1 and create something isomorphic. So let's recall that Z2 cross Z3 is isomorphic to Z6 by a previous result. So in fact, one standard way of writing this would be Z10 cross Z30. So there what we did is combined this Z2 and this Z5 into Z10. Again, GCD of 2 and 5 is 1, so you can combine them and you get an isomorphism. And then after that, we combined the Z2, Z3, and Z5. And then we could do the same kind of game over here, and we would end up with Z5 cross Z, let's see, what's left over? It will be 60. Okay, so that's from leaving this Z5 on its own and then combining everything else because the GCD is 1. Then what could we do here? Well, perhaps we'll combine the Z2, the Z3, and the Z25 because their GCD is 1, leaving us with Z2 cross Z150. And then finally, these three numbers are all relatively prime, so that means we can combine them into a Z300. So there's our cyclic group. And now I'd like to notice that sometimes this is given to be like the standard way of writing it, and I think it's nice or considered nice sometimes because you've got these numbers that all divide each other, kind of building up from the left to the right. Notice that 10 divides 30, and then 5 divides 60, and then here 2 divides 150. Okay, so now I'm going to leave you with some warm-ups. So here are two nice problems. The first is to find all abelian groups up to order 20, and the second is to find all abelian groups of order 720. So here there's a bunch of groups to check out, whereas here there's a single one, but the number is bigger. Finally, what I really mean by all abelian groups, I really mean up to isomorphism. And of course, you're essentially only using this fundamental theorem of finite abelian groups. And that's a good place to stop.